Hello and welcome to Tensar Ground Coffee, a few minutes on ground engineering to enjoy while having your coffee. Well, continuing with the Ask Andrew series on ground engineering, we received another question by letter this time. It's always good to get a physical letter in the post. This one's from Sandy Gravel, and she asks, what is a reinforced soil wall? Okay, thanks Sandy. That follows on very nicely from the previous episode. So let's go over to the flip chart, Brian, and let's explain what a reinforced soil wall is. Now, in the previous episodes we learned about what a retaining wall is and the different types. And we saw that one of the types, just at the end of the previous episode, was a reinforced soil wall. So that's where we have fill material. So you can only construct it with fill material, you can't put it in natural ground. So let's imagine we need to build this layer up here, and here is the natural ground level. So we want to create a vertical slope in a fill material. This could be for a bridge abutment, it could be a sea wall, or for any reason that you might need to create a retaining wall on a higher level here. For bridge abutments, not only can it be used to support the soil around the approach embankments, it can also be used to support the weight of the bridge itself. That's a true bridge abutment. So the bridge could go on here, so the bearings of the bridge would be supported by a foundation directly on the reinforced soil wall. And we've even constructed integral bridges as well, where they have been supported on reinforced soil abutments. So it's possible even as a true bridge abutment. Now there are several names thinking about it, so you don't get confused between the names. They all mean similar things. There's the reinforced soil wall, RSW. You also see MSE wall, which stands for mechanically stabilized earth. And of course there's reinforced earth as well. They all work in a similar way. Within the fill material that you build up here, as you build up the layers and compact, you are laying this reinforcement in here. Now, it's not a new idea. There are even sections of the Great Wall of China that were constructed in a similar way to this. But in its current form, that was pioneered by Henri Vidal in the 1960s, using steel strips for the reinforced earth concept. Things have evolved a bit since then. We now have, instead of steel strips, you can have polymers like this. This is what Tensar supply. There are certain advantages with this approach. In particular, it's more resistant to certain environmental conditions than the steel strips, but also you notice it is quite flexible. That actually can be a good thing. You get more mechanical stabilization from the aggregate interlocking with all the ribs of the geogrid. I'll talk a little bit more about that in a minute. So this is the reinforcement that goes along here. These are the red lines. It's reinforcement like this, that's put in layers. So as you place the fill, just take out the slack. We don't want to install it with some slack in it, so just pull it a little bit tight, and then you will have quite a stiff, strong structure to support whatever loads you have on the top here. So, as I said, they could be used for sea walls or bridge abutments, or for just as a general retaining wall. Now let's look at the components of the reinforced soil wall. You have the facing here. That is generally made from precast concrete, so there's no formwork and curing to undertake on site. Could be precast panels, or it could be smaller blocks. So you have a blockwork facing. The advantage of those is they can be handled manually, so the construction is very straightforward, no heavy equipment required. For temporary structures, it could even be a steel mesh. These facings are designed to allow some movement, so you may get some settlement of the foundation or the fill just a little bit, and this can accommodate it, whereas as a a more rigid structure may crack due to some movements. This can accommodate those movements, and it is for that reason that these walls perform particularly well in seismic situations. There have been many examples where there have been severe earthquakes in areas where these structures have been built, and they have performed remarkably well, whereas nearby a more conventional rigid structure has failed. So the reason they perform so well is because they're strong but also ductile. They can accommodate quite a lot of strain. Then there's the fill material. The higher quality material, a well-graded granular material, can be used under bridge abutments and for very high walls. You can also use lower quality fill if you have some Site 1 material on site. That can also be used, that's taken into account in the design, but it is possible to build these structures out of lower quality fill as well. That's another reason why they can be very economical. But in the high quality fill, there's no theoretical limit on the height. The Fujira walls, for which we did a tensile ground coffee episode recently, they're 60 meters high and constructed in this way. So there's no real limit. The restriction really comes down to the natural soil, the foundation soil. Is it strong enough to support the weight of all this reinforced soil mass? So it's very important to check the in situ foundation conditions. Okay, let's talk a little bit about the design, how they are designed. If you want to check for deformation, serviceability limit state, you can do it in finite element analysis. We can advise you more about that. For ultimate limit state, we use conventional limit equilibrium methods. So that involves some some assumed failure mechanisms, such as something like a two-part wedge. So we check a failure mechanism such as this, and then we are checking the tensile strength of the reinforcement, that it can resist that failure mechanism. So that's how they're designed conventionally. But when we monitor the performance of these walls on site, we see that they way outperform what is predicted by the design methods. There's something else happening in reinforced soil walls, and that brings me back to the mechanical stabilization, that when you have a granular material interacting and interlocking with this geogrid, it actually restricts particle movement and rotation and gives the fill extra strength. And that's how we explain the higher performance of these sorts of walls. So I'm going to touch on that in a webinar that's coming up. Look out for that, where I'm going to talk about the benefits of mechanical stabilization in structures such as these and other applications. Okay, that's just a quick overview then of the reinforced soil wall. I hope that's answered your question, Sandy. That's all for this episode of Tensile Ground Coffee. Thanks for watching, and see you next time.